Okay, hello everyone. So welcome to the last video for this week, video 10. And so I want to continue on with using the derivative to approximate things in a little bit more generality than we did earlier, and then do some applications to position, velocity, and acceleration. Those physical things that keep bringing up, we'll finally do some examples with those. And we should be in good shape for this week at that point. Okay, and the cat is here again. All right, so we can use, sorry, cat. You can see what's going on, okay. You can go here. Here's a good place. Go back. Okay, we can use the derivative to approximate not just the function one value beyond where we are. So in the previous video, we talked a lot about marginal cost and so for marginal revenue, and we saw how we could use the marginal cost to estimate the cost of producing X plus 1 items if you know X, the cost of producing X items. So like how much is it to cost, how much would it cost really to produce one more item? But we can do this like not just for one, but sometimes an arbitrary number of items, as long as we don't go out, don't take too big of an estimate. Don't go too far out from the point where we are. So the way to say that precisely is we can use the derivative to approximate the value of f a plus h from f of a for small h, in the quotes, both when h is both positive and negative. And so the formula we have for this is the analog to like kind of a little bit more of a general version of formula star. So it's that f of a plus h is approximately f prime of a times h plus f of a. And the idea is, again, is that this is just using the tangent line. So if you have your function f, here's a, here's a plus h, here's the point, so that's the point a f of a, this is the point a plus h, f of a plus h. So here's my tangent line. Right, so this value here in purple, this is the value of the tangent line at a plus h. So this is the point a plus h, f prime at a times h plus f of a. And what we're saying that if the h isn't too big, right, if the h isn't too big, then this value, it's a bit harder to write out now, f prime at a times h plus f of a, right? This is not too far off from the value you actually want, which is this pink one, f of a plus h. So long as h isn't too big, right? You can imagine that, as the curve keeps bending upwards here, and the tangent line kind of goes on its merry way, as you go further and further out, the tangent line values will diverge substantially from the function values. And this will become basically a useless approximation. But so long as h is small, this is okay. And you can kind of see, so what I've drawn here is I've drawn it for positive h. You could also do it the other way. I could have also taken my h to be negative and gone to the left, right? And gone along the tangent line in the opposite direction, right? And then my point would have, my purple point, sorry, purple, would have been down here, right? And then the f of a plus h would have been, say, there. Okay, so we can go both ways along the tangent line to estimate the function values, so long as you don't go too far away from the point A where you start. Because eventually, unless your function is almost a line, eventually the curve is going to get far away from the tangent line, and this approximation will not be that useful. But it gives you kind of, for small values of h, a nice like approximation, a fairly good kind of back of the napkin approximation. So I'll call, this is our new formula star. Okay, so this is, so in the previous video, so this is, I should just say, so equation star here generalizes the analogous equation, the similar equation from video 9, which is just this equation with h equals 1. Okay, so let's do some applications and examples. Here's an example. So suppose f of t gives the population in millions, sorry, after t years. And let f of t equal 45 and f prime at 15 equal 1.3. And we want this example wants us to ask answer the following question. So question 1, what does f of 15 equal 45 actually mean in practical terms? What does that mean in practical terms? 2, what does f prime of 15 equal 1.3 mean in practical terms? And 3, estimate the population after 15.5 years. Okay, so that's what it wants us to do. Okay, so the first two questions, we can just kind of, just remember what the function means and read off from this data, right? We can just use the definition of the function along with the definition of the derivative to understand what these things mean. So f of 15 equals 45. So f of 15 is telling us the population in millions of years, in millions of people after t years. So f of 15 equals 45 means that after 15 years, the population is 45 million. So answers. So to 1, after 15 years, the population is 45 million. Okay, so what about, so that one's easy, that's a layup. What about number 2, what does f prime of 15 equal 1.3 mean? Okay, so let's think about this. So what's the derivative? So the derivative is the rate of change of f with respect to t. So this is the rate of change of the population with respect to time. And it says f of 15, f prime of 15 equaling 1.3 says that at 15 years, the population at that instant, at 15 years, is increasing at a rate of 1.3 million people per year. So, oops. F prime of 15 equals 1.3 means that the population is increasing at a rate of 1.3 million people per year after when 15 years have passed. Okay, so the derivative is something about the rate of change of population with respect to time, and exactly after 15 years, the population is increasing at a rate of 1.3 million people per year. So let's clean that up there. Okay, now the estimate. So estimate the population after 15 and a half years. So we know, what do we know? So we know that the population at 15 years, right? This we were told was 45. And we know the derivative, the rate of change there. So we can use formula star above. Where did it go? There it is. Right, we can use this formula star with a equals 15 and h equals 0.5 or 1/2. And we will get the estimate. So we can use formula star with a equals 15 and h equals 0.5 to obtain the estimate. Let's see, so if we do that, so we have f prime, so f of 15 plus 0.5 is approximately equal to f prime of 15 times 0.5 plus f of 15. So we just need to work out this quantity here. So it's 1.3 times 0.5 plus f of 15 we were told was 45. And so if we work that out, if we work that all out, we get approximately, so we get 45.65 million. So we can say that, oops. So we can say that after 15 and a half years, the population will be approximately 45.65 million. Okay, so that's a nice little application of this more general approximation formula. Let's do another example of this type of thing. So this is more abstract, so this is an abstract example. Okay, suppose we are told that f of 50 equals 75 and f prime of 50 equals 5. Approximate f of 52, and f of 47. Okay, so maybe I will do one of these and you can try the other. So let me do 47 because that one is involving a negative h instead of a positive one. So we haven't done one like that before. And then the 52 I'll leave to you. And it's very similar. And there's tons of these on the homework on MyLabs Plus or MyLab Math. So let's do f of 47 and I will leave you to do f of 52. Okay, so for f of 47, you will again use this formula star from the beginning of the lecture. I'll write it out again. I'll write it out again so you don't have to, I don't have to scroll up. So f prime at a, sorry, f of a plus h is approximately equal to f prime of a times h plus f of a, with a equals 50 and h equals minus 3, right? Because what we want to estimate is 47, which is 50 minus 3. And we know the value of f at 50 and the value of the derivative at 50. We are given that information. So that will serve as like the point where we ground the estimate, and then we'll just go 3 to the left now instead of to the right. Like I said earlier, you can do that as long as you don't go too far away from the point you start at. Okay, so f of 47 is approximately equal to 5 times minus 3 plus f at 50. Right, so this is, so I should say this, I skipped a step. So this is f prime at 50. But f prime at 50 is 5. So 5 times minus 3. And then f of 50, we're told, is 75. That's all up there. Right. There it is. So let me clean this up a bit. And so this is 75 minus 15. And so that's 60. So f of 47 is approximately 60. Okay, so now we can, hopefully this isn't too dry. Yeah, I think you see some examples in the homework where you do some cool estimates with cost functions, with dosage functions, and things like that, using these ideas from this section, from this part of the video. So the final thing for this week is to do a little bit some physics problems, which I love. Hopefully you love them too. And kind of tie in what I was saying at the very beginning of the video 8 about higher derivatives that, so this is physics. We start off with the position function, s of t, as a function of time. And we differentiate that, and we get the velocity function, which is the rate of change of position with respect to time. And if we differentiate the velocity function, we get the acceleration, which we think of as the second, resulting in differentiating the position function twice. So it's the second derivative of position. This is acceleration. And this is rate of change of velocity. With respect to time. Okay, so this is what I went over all of this at the very beginning of video 8, but now we're tying this all back together. At the very end of the week, we're going to do some actual concrete examples with solving physics problems, and this will allow you to do all the remaining homework in section 1.8. So the ordering is a little weird, but we kind of took a break to a little bit understand how do you do approximations. Some of this will come up on the homework. And now we're going to come back to where we started at the beginning of the week and really review our knowledge of higher derivatives and use that to solve some really cool physics problems. So there's two that we're going to discuss here. So first example. So a helicopter is rising straight up in the air. Its distance t seconds from the ground. After takeoff is given by S of t equals t squared plus t. And so sometimes it's good to kind of draw a little bit of a picture of the situation when you're dealing with this physics things, because it sounds silly, but it's important to remember which way is up. Because that tells you how to orient your position coordinates, what's positive direction and what's the negative direction. So, which is important for more complicated problems. So here we have the ground, right? Oh, sorry, some ground. And I can even color it like, this ground. And then the helicopter is taking off. I mean, I'm not going to be able to draw a helicopter, but it looks something like this. And it's rising straight up, right? So the position coordinate S of t is positive in the upward direction. And so what this is telling us, what this means is that after t seconds, the height of the helicopter is t squared plus t. So in the upward direction is the positive direction. Okay, so that's kind of just good. Have a little sketch. What are the coordinates? Which way is up? Which way is positive? Which way is negative? Okay, so here are the questions we want to answer. How long will it take the helicopter to rise 20 feet? Secondly, number 2, find the velocity and acceleration of the chopper when it is 20 feet above the ground. Okay, so we have everything, we have all the tools to be able to do this. So let's answer the first question first, and this is where the picture is kind of comes in handy. I realize my helicopter maybe looks like some kind of a bug, but if you get beyond that. So what is the first question asking? It's asking how long will it take for the copter to rise 20 feet? So it means, what will the value of t be when this function, the height of the helicopter, is equal to 20? That's what it's asking. What is the t when it's gone 20 up from the ground? So let's put that into mathematical terms. I mean, you're going to see here that half of the battle with these things is taking the word problem, the language of physics or the economics or what happens, population, whatever happens to be the application, and turning that into a mathematical statement where we can easily solve using the calculus techniques that we now know. So answers to 1, we need to find t, the t such that S of t equals 20. So this amounts to solving the quadratic equation, right? T squared plus t. Remember, S of t is t squared plus t, you see above here, right? So this amounts to solving the quadratic equation, t squared plus t equal to 20. So that's equivalent to the equation t squared plus t minus 20 is equal to 0. And this actually factors easily. So it's t plus 5, t minus 4 equals 0. And notice that we have two solutions. T equals minus 5 and t equals 4, right? But only one of these solutions is actually admissible for the problem, because you have to think about it this way, we only start observing when t equals 0. So this t minus 5 solution has to do with before our observations start. It's not admissible in this situation. So the only solution that's admissible is for the positive time. So the solution t equals minus 5 is inadmissible because it occurs before we are observing the helicopter. And the solution we want is the positive one. Is t equals 4. So it will take 4 seconds. So in putting it into words, it will take 4 seconds for the helicopter to rise 20 feet. Okay, so that's what we found. So negative time means before you're actually making the observation, just ignore it. I could get into this, any weird physics about what that means, but it's just before we start observing at t equals 0, and then so the equation doesn't work for time before t equals 0. Okay, and so now we also want to define, right, what's the next thing we want to do? We want to find the velocity and acceleration of the helicopter when it is 20 feet above the ground, right? So in terms of our language of derivatives, right, where did that go? Right, so if we want to find the velocity when it's 20 feet above the ground, we want to find v of 20 or s prime of 20. And if we want to find the acceleration, right, when it's 20 feet from the ground, we want to find the derivative velocity at 20, or equivalently, the second derivative position at 20. So when you're doing this, because the derivatives come in sequence, it makes sense to first find a velocity, right, at 20, because that's the first derivative position. Then you differentiate the velocity function, produce the acceleration function, and find that value at 20. So that's the procedure. I'll write it out down here. Okay, so let's see what I can say. So we start by finding the velocity function, since v of t, this velocity function, is the first derivative position. So we're told that s of t is t squared plus t. So s prime of t by the power rule is 2t plus 1. And therefore, and that's the same as the velocity function, right? Therefore, v of 20, the velocity at, the velocity at 4 seconds, right? It was at 4 seconds, is 2 times 4 plus 1. So the helicopter was at 20 feet at 4 seconds later, is 9. And what are our units here? Feet per second. Okay, now, so that's the velocity at when the helicopter is 20 feet above the ground after 4 seconds. So recall from part 1. that the helicopter is at 20 feet, is 20 feet off the ground at 4 seconds. Okay, and now we find the acceleration function. Okay, to find the acceleration function, we have to differentiate the velocity function. Velocity function with respect to time. So you have, okay, the derivative of velocity is v prime at t, which will be a of t, which will be the derivative of this 2t plus 1. But that's just, derivative of 2t plus 1 is just 2. So that's actually 2 feet per second squared. And notice now, this is constant acceleration. Constant acceleration. So we don't have to worry about evaluating this at 4. I mean, it's the same everywhere. So when the helicopter's at 20 feet, t equals 4, a of t is 2 feet per second. And you can kind of say, in fact, the acceleration is constant throughout the motion. So that's the kind of thing that that can happen in one of these mechanical. Often in these mechanical problems, you'll see much of the motion as constant motion with constant acceleration. Okay, so let us do, at least I'll start the next problem. I'm not sure I'll finish it all, but I'll kind of tell you how to go about doing it. And we can talk about it in the live meeting if you like. So kind of example. So a toy rocket is fired straight up from the air. And its height is given by S of t equals 240t minus 16t squared feet in feet after t seconds. And again, we can draw a little picture if you like. Maybe some big green grass here, that's the ground. And the rocket is fired up right from the ground. And the position is again in the upward direction. The positive direction is the upward direction, right? Okay, so here's the first question, and I'll just, I won't write them all out now. What is the rocket's initial velocity? Okay, so initial velocity means the velocity at t equals 0, i.e., what is the velocity of the rocket at t equals 0? So to do this, we need to take the position function, right? Differentiate it get the velocity function, and then plug in 0 to see what we get. So we need to find this, to find v of 0, we need to first find v of t by differentiating the position function. That's here. And then we can evaluate the result at t equals 0. Okay, so what are we told here? So we have S of t equals 240t minus 16t squared. So S prime of t is the derivative of this guy, 240t minus 16t squared. And then again, just like power rule and sum rule, this is 240 minus 32t. So the velocity function is 240 minus 32t. So at t equals 0, the velocity at 0 is just 240 feet per second. Not too bad, not too shabby there. And we can kind of do the next problem. So the next problem is just kind of about the velocity function. So what is the velocity after 4 seconds? T equals 4 seconds. Okay, so we need to compute this. So here's our velocity function. We found it in the first part. So for this, we evaluate the velocity function. We found in part 1 at t equals 4. So what was it? So it's v of t was this guy, 240 minus 32t. And so v of 4 is 240 minus 32 times 4. Let's work that out. And it equals 112 feet per second. Okay, so that's not too bad. Just clean that up a bit. Okay, so the third question is, what is the acceleration when t is 14 seconds? Okay, so to get the acceleration when t is 14 seconds, right, we have to take the velocity function that we found here from which we found back in part 1, differentiate it with respect to time, produce the position function, and then evaluate that at t, produce the acceleration function, and then evaluate that at t equals 14. So we first find the acceleration function. By differentiating v of t with respect to time. And so you get d dt, and v of t, I have to go back up and see it, there it is d dt of 240 minus 32t. And this is quite easy. This is just minus 32, right? The derivative of 240 is 0, and the derivative of t is 1. So you just get minus 32 feet per second squared. So actually, you see, again, we have constant acceleration. So a of t is v prime of t is a constant function, minus 32 feet per second squared. So we don't have to plug in 14 because it's always minus 32. There's nothing to plug in to a constant function. The value is always minus 32. But we should say, so when t is 14 seconds, the acceleration of the rocket is minus 32 feet per second squared. Now the negative here has some meaning, right? So let's kind of go back up to this little picture that I drew. Where did it go? With the rocket here. Back up we go. Okay, so now the rocket, the positive direction is the upward direction, right? So the position is positive in the upward direction. So the fact that the acceleration is negative or is always negative, right, means that actually the acceleration is acting in the other direction, downward direction. So that the rocket, after you initially launch it, is just slowing down. It's going to come back to Earth. And that value minus 32 feet per second is what's often called in physics feet per second squared. That's what's called in physics the little g. It's the acceleration due to gravity. So and that acts down back to pull the rocket back to the Earth, to the ground. So the acceleration is acting in the negative direction against the initial motion, and it's going to slow the rocket down over the course of its motion and cause it to fall back to Earth. And it's exactly the acceleration due to gravity, which is pulling that rocket back to Earth. So that's what's going on. And the next two problems, I'll just let you kind of figure this out. But so what time, oops, I'll tell you how to do them though. Well, what time will the rocket hit the ground? Well, I guess I can do this very quickly. So, okay, so we need to solve the equation. The quadratic equation. S of t equals 240 t minus 16t squared equals 0, right? The ground is position 0, right? Where the rocket starts off. So there's going to be two solutions, and one of them we can kind of ignore and understand what it means, but so we need to factor the equation. (240t minus 16t squared equals 0. So we get t, and I can probably, let's see, 240t minus 16. Oh, sorry, 240 minus 16t equals 0. So you have two solutions, t equals 0. And the other is t equals 240 over 16, which I think actually is a whole number. Let me check. No, it's not a whole number. Sorry. It's, what is it? So let's see. It is a whole number. It's 15. Okay, so there's two solutions, 0 and 15. So this we kind of ignore because the t equals 0 is when the rocket started launching, right? So this is when the rocket was launched, and we're interested in when it comes back, and that's this one. So this is the time the rocket was launched. And the bigger number is when it falls back to Earth. And so this is the time it comes back down to Earth. So the rocket hits the back, returns to the ground after 15 seconds. After 15 seconds. And what's the velocity? So 5, what's the velocity of the rocket when it hits the ground? So we need to take, we have the velocity function. Where did it go? There it is. Copy this. Right, so we know the velocity function is here, and so we just need to find, we know it hits the ground after 15 seconds, so we just need to plug 15 into this. So the velocity when the rocket hits the ground, so the hits the ground is v at 15, so it's 240 minus 32 times 15. And if you multiply that out, that is minus 240 feet per second. Okay, so that says, and this kind of makes sense, the velocity is negative. What does that mean? So that means that the moment the rocket hits the ground, right, it's traveling back down to Earth, right, in the negative direction. The positive direction, the positive rate of change of position is upward, right? If the velocity is negative, right, that means that the rate of change of position is in the opposite direction to up, namely down, which we'd expect that when the rocket's hitting the ground, it's traveling downward. So we would expect there to be a negative answer for the velocity, and there is. So that's what we would see. Okay, so we've done a lot this week. That's all for this week. There's a lot of homework problems like this. So make sure you follow along, take a good stab at the homework, and I'll be more than happy to help you with these problems. They do take some getting used to. There are steps involved. And I think, like I said, sometimes the hardest thing is translating things into the calculus. All right, so I look forward to seeing you guys in class, and that's it for now.